Okay, thank you. Can you hear me at the back? Huh? Yeah, okay, great. So yes, this will be a bit about implementing languages on the VM. I like implementing languages, okay, so this is my favorite topic. And so what I'll go through generally is a bit about what languages, very little, some of the basic tools that exist in the standard Erlang distribution, okay. There are a lot of other tools you can find on the net, but these are just some of the standard ones. And then I'll show 3 case studies I have done of different languages with different requirements. So there'll be different results in how I implemented them. And also, there will be some techniques that you might enjoy while working. So from my point of view, what languages? Anything in your Erlang application that's written in another language, right? So they can be config files. You can have domain-specific languages. You can, like I've done here, implement other languages, do other front ends for Erlang. If you don't like the existing Erlang front end, you can rewrite your own, right? Lots of other things like this. So my examples are from, well, mainly from the other languages bit. And there exist a number of basic tools in the standard distribution which you can use just to get you going. So, for example, there's Leaks, which is a lexical scanner generator. There's Yek, a parser generator. There are a bunch of syntax tools for managing Erlang code, Erlang abstract code. There are XML parsers. There's one in the system, XML-Earl. And of course, one of the most important one you can play with is the compiler itself, right? The compiler is not a black box. It's not just sort of a black box, you put a file in one end and get a file out the other. You can actually go in and do things with that, with the compiler. So to start off, Leaks, well, it's a lexical scanner generator. And it's based on Lex and Flex. So what it does is, it uses regular expressions to define tokens. So you can define your tokens in Leaks. You can use it to generate code which will then tokenize your input and return a sequence of tokens. So it's this thing of collecting characters together into tokens. Right? It generates by default 3 scanning functions to use. There's one for direct use, which you can just meant to just call directly. You have a string, I call my scanner string, and it will just return a list of tokens from that string, or an error if it bombed out. There are also 2 functions which are meant to be used with the I/O system. Now, the I/O system is a pretty neat thing, but you have to know how it works and how to interface it. And Leaks generates 2 functions which do that. You can use them yourself. I'm not going to exactly describe the interface. It's in the documentation, but you can use it yourself, but they're intended for the scanner generator. So what does a Leaks file look like? So here we have a very simple example of a Leaks file. It's generally called a .xrl file, containing information. So at the beginning, under the definitions heading, I can define a number of macros. So here I've defined 3 macros, U for uppercase letters, L for lowercase letters, and D for digits. And we're using regular expressions here. So I don't have time to teach you regular expressions, but we're using regular expressions. And it's the general standard POSIX regular expressions, not the Perl ones. They are different. Unfortunately, they have different semantics, and the Perl regular expressions wouldn't work in this context. So for example, the uppercase says, the U macro here says it's a letter, or it's a character between A and Z, capital A and Z. And the lowercase is it's a letter between a little a and Z, and D is a digit, which is a character between 0 and 9. So that's what that regular expression construct means. And using that, I can define tokens. So for example, the first one here is the Erlang atom token, the unquoted atom token. So we can see, well, we wrap the macro in curly brackets, which says take that macro, and we can see that means it starts with a lowercase letter, and then it consists of either an uppercase letter or a lowercase letter, or a digit, or an underscore, and the star at the end means there's zero or more of them. So this is our simple definition of an atom. So here we've defined what an atom is, and when it finds an atom, here we have an expression saying what it's supposed to return. So it's going to return a tuple, which is called a token, which is going to tell the leaks that this is a token, and then here we have the actual value of the token. So we're returning an atom. This is actually what's returned from the standard Erlang parser, or the Erlang scanner, by the way. We've got a token. We have some predefined variables, token line here and token cars. And token line's the line which the token occurred on. And token cars is a list of all the characters it found in that token. So in this case, I just take the list, I make an atom, and I return the tuple atom, the line, and the actual atom itself. And I'm wrapping in a token saying it's a token. I can do the same thing for variables. So a variable starts with an uppercase letter or an underscore, and it contains uppercase, lowercase, letters, digits, or underscore, 0 or 1 of them, 0 or more of them. And when I get one, I will return a token. This will be the var token on this line, and that's the actual value of the token. Or I can define a comment, which starts with a % and contains any number of characters which aren't the new line character. And it returns skip token saying, I don't want this one, just throw it away. If I want to return my comment token, I can, of course, do that. So what I decide to do is up to me. And yeah, so if I run this through leaks, it will generate a file. So if I, for example, put it in my scan.xl, I run it through leaks, and I'll get a file, myscan.earl, which I then can compile, and I can use. And it will just do this, which is not really very helpful, but it will work. Yeah, this format of tokens, where you've got some form of token class here, the line it's on, and the actual value, that is quite commonly used, and it's actually what YEC, the next tool we're going to look at, expects for its input formats. So if I use this and generate another format, which is perfectly free to do, I can do anything with it, I won't be able to pipe it into YEC, which is also very nice. So after I run this through, I'll get my file out, I'll have my myscan.earl, I can compile it, and then I can call the 3 functions in it. So the direct usage one is string, and I call that with a list of characters, a start line, and it will return, OK, a list of tokens, and the end line. So it keeps count of lines in there. So every time it hits a new line, it'll increment the line number and things like this and keep track of them. And if you've got a token which spans over multiple lines, you'll get back the line number of the first line the token occurred on. So I can use this directly to get back just a list of tokens. If there's an error, it'll return the tuple error, what the error was, and the ending line number again. If I've written my scanner and I want to put it into the I/O system, for example, use it directly against a file, there is no direct call to do that in the system. Right? That's one of the things missing in the I/O system. It's been missing since the I/O system was written and just never got added. Right? But it's easy. So I can do an I/O request here into my I/O device, my file, or whatever it might be, or TCP characters, or whatever it might be. And the request is a get until. The second one here is a prompt. Assuming I'm reading against a file here, I don't have a prompt. It's this module calling this function with these arguments. So if I've written my scanner myself, or any handwritten, I can still use it in the files in the I/O system, calling it this way. I don't intend to go through the I/O system. If anyone wants to know more, ask me afterwards. The I/O system is really neat, right? It's extremely dynamic. You can basically do any I/O towards anything, right? You need to do it the right way. So you've got these 2 functions, token and tokens. Token's obvious. It gets back the next token, right, in the I/O system. So you can do call token, get one at a time. tokens, that scans, returns you all the tokens up until the end of file, whatever that might exactly mean, or until it gets back one of these things where it says end token. Right? So if we're talking Erlang here, dot is a typical end token. So if we do tokens on, if we're doing Erlang, we'll get back all the tokens up to and including the dot. Right? If we don't have an end token, we'll get all the tokens up to and including the end of the file. So it's just a nice little hack written in there which fits Erlang and a few other languages as well. Okay. So that's that. So this allows us to scan it. It's simple. It can't do everything Lex or Flex can do, but it can do quite a lot. Unfortunately, yet it can't detect beginning of line and end of line. It's almost there. And I do have a patch which will actually give you the column the token starter on if you want that as well too. I'll just have to fix up all the tests and stuff like that before I can put in the system. It works. So that's leaks. Right. So this is the first step in parsing our language. We now can get tokens. And there is a built-in parser generator, YEK. It's an LALR1 parser generator. It goes from left to right, but builds it from right to left. And it's one token look ahead. It's based on YAK. It's a similar idea to the YAK, the standard YAK parser generator. And it generates parsing functions as well, but only generates one. Right? It generates the function parse, which you pipe in a list of tokens and will return what you told it to return. Very simple. So we've got a YEK example here. Here's a very small YEK file which will parse simple arithmetic expressions. So we say the non-terminals, that's the thing that's in the middle here, which are expressions, terminals. E is expression, T is a term, and F is a functor here. Also the terminals. These are what I get in from the outside. So I give it a list of tokens, and these tokens will be the type plus, star, left, right bracket, and a number. So I define expressions, an expression plus a term, or expression minus a term, or it's just the term itself. And or a term is a term times a functor, or a term divided by a functor, or just, and the functor is just a number, or an expression with parentheses around it. And doing it this way, I get the left to right, the left priority, and the right priorities of the operators. So I can generate this, and I say the root symbol is where I want to start. I bung this into YEK, into a YRL file. It will generate an URL file, which I then can compile, and I'll get the function parse. I haven't said it, but shown it, but both leaks and YEK, you can put Erlang code in there as well. So if you want a big example of a YEK file, go in and look in the standard distribution, because there is the definition of the Erlang syntax in one.yrl file. It's quite a lot. So that's nice. So now with this, I can quite easily pass my my code, my input. LALR1 parsers, they manage quite a large set of languages, but not everything. And there are a few problems you run into. When you write your description, you'll typically get things like shift-reduce errors. And they're not actually errors, but depends how you look at them. That means that it looks at your grammar, and it can't, in some cases, it can't decide, do I collect more characters, or more tokens, which is shifting, or I try to do something with what I've got, which is reducing. And by default, it will collect more. And that is generally what you want to do. So I think in the Erlang syntax, there are 2 or 5 shift-reduce errors there. That's nothing critical. That's not uncommon. That's nice. But what's worse, you can get reduce errors. And that's typically the thing. The parser generator is looking at your grammar, and it says, when I get here, I cannot determine what I'm going to do. I cannot take one token and decide if I'm going this way or if I'm going that way. I give up. I generate, excuse me, I generate an error. And the typical case is if you've got Erlang, for example, when I define an expression, I would like to write it something like this. I mean, it's very simplified. I would like to say it's a pattern followed by an equal sign followed by an expression. That's how I'd like to do the pattern matching the assignment there. But I can't, right? Because the pattern is so close to the expression that Yek can't decide which to go. It cannot just say by doing one step look ahead saying, I'm now doing a pattern or I'm now doing an expression. Because if you think about the pattern, it's a subset of the expression. So Yek cannot decide. It says, I give up, I give a reduce error. And they're not good, because I can't go on until I solve that. And the typical in this case, I write it like this. I say an expression, there's an expression followed by an equals followed by an expression. In that case, it's happy, right? Because then it can work out, it's just expressions, and it's an expression followed by an equals, I can do that, and there comes another expression, it can do that. So it works. But that means the grammar is going to allow things which I don't intend there. So I can write a function call equals a function call, which is not allowed in the grammar, not allowed in the Erlang syntax. So I have to put somewhere later along the line, I actually have to check the left-hand side here and see if it actually is an expression. So that's what's done. In the Erlang syntax, you have this exact problem, and it's checked in the next parse. One of the first parses of the compiler called Erlang, which checks that. That will find those errors. That is a problem when you have just one character look ahead. Yeah. So that's leaks and Yek. And they're nice, because they give you an easy start. And for example, look at the Erlang syntax. It's in the distribution, in the standard libsrc directory. It's big. You wouldn't really want to write that by hand. Definitely not. There are other tools. There are syntax tools. These are tools for creating and working with Erlang abstract syntax. I'm not going to go through those. I think Richard's doing that after the break. We're talking a bit about that, so I'm not going to do that. And there are other parsing systems that aren't part of the Erlang distribution. There are a number of peg parsers, and just another type of grammar. So I'm not going to talk about those either. So now we've got our stuff in, we're parsing it, we've parsed it, we've got our abstract syntax, now we want to do something with it, right? And one way of doing something with it is compiling it. And we've got the Erlang compiler, which compiles down to the Beam code, which is very nice. So we can do things with that. And it as I said, it's not a black box, it is quite open. It can, for example, work on both either files or Erlang abstract code, and it can generate Beam files, or it can generate binaries. So you can take something, an abstract parse tree, directly in memory, compile it into a binary, and it's still in memory, and then you can do things with it. Send it to other nodes, or load it down, or install it in the system. So if you're generating Erlang code, say from your syntax, you never have to generate a .erl file to compile it. You never even have to generate a .beam file to get it into your system. You can do everything in memory, compile it straight off. But it also has a internal language called Core Erlang, which is a very nice intermediate language. Erlang, for all its beauty, is not quite simple and regular. Right? It's not that bad, but it's not quite simple and regular. Core is. It's a simple, regular, functional language, and I think anyway, it's much easier to compile to than doing to Erlang. I mean, there's nothing stopping you doing to Erlang, but going to Core is easier. And internally, the Erlang compiler looks something like this. So there are at least 5 parsers in the Erlang compiler. This is just generating Beam, right? So we're getting Erlang in from the left here, and first we're doing some pre-expands, which basically just looks, well, before we've got this stage, we've done the macro expansion. This is even after done the macro expansion even before this. Here we've actually done the parsing, and we've done any parse transforms we want to do. Then we go into pre-expand phase, which looks at mainly at records, and expands records and removes all the record stuff, and does a bit of adding a bit of information about the system. And then we go into a pass called V3 core. V3 means it was version 3. Right? There's no greater significance than that. There was a version 2 and a version 1, but they've gone now. And that generates core Erlang. Okay. So after the Erlang's gone through that, after it's gone through V3 core, we've got core Erlang. Right? So this is the core Erlang pass here. And for core Erlang, there are a nice bunch of optimizations. So most of the optimization work in the compiler works on the core level. So if you're compiling things, don't compile to the Beam assembler code, because then you have to do everything yourself. Right? You've got nice things down here. And then it goes to kernel, which does other things like pattern matching optimizations. It lambda lifts all the local functions and does other things. The life looks at the variables, looks at the lifetimes of the variables to work those out. And then the code just generates the Beam code. Okay. So core. It's a nice, simple functional language. And to be different from Erlang, it does have sort of more normal lexical scoping, which is actually easier to compile to. It's easier to work with. But it's just the basic language, right? So there are no records in there. There are no things like Lisp comprehensions. They've all been compiled out in the V3 core level. So it's just functions, just raw, basic, simple functions. But it does have patterns. So it does do pattern matching at this level. So you can put patterns in, which is a great win. Because one of the things afterwards is a pattern matching compiler, which is quite optimal in handling patterns. Although semantically Erlang does clause, 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 when it's pattern matching, internally the compiler does quite a lot of work to get rid of the clause, 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 and do it much more efficiently. It looks like it's doing it, but it's not internally. And that's something you want. And as I said, most optimizations are done on core. And another feature is the Dialyzer speaks core. So if you generate core Erlang, then you can put your code in and get it into the Dialyzer and have the Dialyzer check your code together with any other code right, in the system. I'm slight prodding here to Costis and the Dialyzer group to open up the front end slightly so make it easier to load in files of other types. But if it speaks core, the Dialyzer can work with it. Except patches. Yeah, well, one of these days. One of these days, yes, I know.
At least you have to send a specification of what you want to do.
Oh, specs, okay, yeah, right. You'll get one, you'll get one, you'll get one. But then I can do it. Then LFE can run Dialyzer together with everything else, and everyone, including me, will be happy. So yes, okay. So here's a very simple example of core Erlang. The syntax is rather verbose. There is actually a core pretty printer, and there's actually a core parser as well too. So you could actually write core Erlang directly if you wanted to. But as I said, the syntax is not compact, we'll put it this way. So I've got my standard factorial up here, fac when n is greater than 0, n times fac n minus 1, and fac 0, 0, right? And it generates a function here, fac1, and it's a fun, and the argument's core, and then we do a case here to look at to do pattern matching on the arguments. So one of the things that happens is that all pattern matching is broken out into a case internally. And if it's n and we've got the guard here, then we do this, create a local variable here, and then we apply fac1 to this variable, and we let that in, and then we set that variable to that, and then we return that value there. So the compiler breaks all down, explicitly handles all nested expressions and breaks them down and flattens everything out. Amongst other things, the reason the Erlang compiler does it, amongst other reasons, is that it enforces the left to right evaluation of Erlang. Of course, it's actually not defined which order you take things in, so forth. A thing to remember if you're doing this yourself is to try and do exactly the same thing, because most of the optimizations assume this structure. Right? So if you don't do it, then you don't get some of the optimizations. Fortunately, it won't do anything wrong, but just won't optimize it. So you can see it's a very simple one. And for example, it's a simple language. This is most of it, actually. You can define local functions. There's a letrec for defining local functions and things like this as well. Seeing it's using case for everything here, it adds on an extra case clause at the bottom here, which says what error it is if none of the arguments match. So in this case, we see it's a function clause error. If this was actually a real case, an Erlang case, it would generate a case clause error. So we're using case for everything, right? We even use case for ifs. Then we get the degenerate case here, where there's no expression and no matching here, just the guards, right? Which is exactly why we put in if in the originally to get rid of that syntax, but it's in here anyway. But it means that it's quite easy to generate this. And there is a definition about this is all record-based, so they're the record definitions in the compiler, and there's also a module called Cerl to allow you to build these things through function calls instead. So it's perfectly feasible to do this. There is also a paper from, when did you write that paper, Richard? Richard wrote a paper describing core. It's long ago, but very little has changed since then. Right? I hit one change between R12 and R13, that's about it, right? So yeah, if you're going to compile stuff, compile to core. It's great. I find it much easier than compiling to Aline. I find definitely you can, for example, compile config files if you want to just compile them down to Erlang code and run them. I think a few applications already do that. I think it's yours and MockeyWeb do that or something like this. So it's really nice. Okay, so they're just some tools, and do it, it's nice. Yeah, okay. So the first example is Lisp flavored Erlang, and it's something I did a while back, and it's still working, and it's still running, and there are no known bugs in it, so if you want to use it. Well, there's one. Actually, there's one. If you're doing nested query list comprehensions, it will not handle that properly. If you're doing simple query list comprehensions, it works, but not nested ones. I'll fix it one of these days. Okay, why did I do this? I like Lisp, right? Simple. And while I don't have anything against the Erlang syntax, I love Lisp. And Lisp provides a lot of nice goodies you can do. It's a real homoiconic language, and it's got real macros. Right? Erlang macros is just a simple token substitution. Lisp macros, you can do a lot of stuff in the macro level. It's very nice. So that's one reason for doing the Lisp syntax at all. Another goal I had was that it would seamlessly interact with a vanilla Erlang OTP. So you could write your LFE files, and they work directly together with OTP. So if you want to write a behavior callback module for gen server behaviors or OTP behaviors, you could write that in LFE and everything would work. So there'd be nothing strange going between LFE and Erlang. You could freely mix them. Yeah, so you could do that. I wanted to make it easy to implement. I wanted a small core language and most of the other things built on top using macros, right? And I wanted to go as fast as vanilla Erlang. Okay, I didn't. If you chose to write your module in LFE or chose to write in Erlang, the speed wouldn't be the reason for choosing one or the other. So yeah, so that meant a few problems. It meant I had to modify a Lisp, because most of the standard Lisps would not fit directly onto the Erlang VM in such a way that it seamlessly interact with it. Right? So for example, no mutable data. They could only use the standard Erlang data types. You have atoms, numbers, lists, tuples. That's about it, right? Binaries, of course. But you cannot do any other sort of user-defined data types. It also meant that if they have records, they had to look like Erlang records. So I could not define Lisp-type records or Lisp-type structs in there because they just have no Erlang corresponding Erlang data type. It also meant, for example, that I needed modules. I could not do packages, for example. I couldn't have a common Lisp namespace package namespaces, because that just does not map into Erlang. You can hack it, but then the interface is not going to work properly. It also meant you wanted Erlang functions, typical Erlang functions. So for example, you could not have functions with variable number of arguments, which most Lisps give you, because Erlang does not support variable number of arguments. Not if you want to do it fast anyway. So you get these limitations. But again, I get the benefit. I can have functions with the same name and different number of arguments and different functions. So it's very close mapping. It also means, unfortunately, macros are only compile time. Because in a real Lisp, the Lisp internals know if a function is a function or if it's a macro. And Erlang doesn't. So I cannot have a macro that works at runtime because there's no way to say what this is. And that's important, not for what it does, but for how it's used. So in Lisp, when the system knows it's a macro and I call a macro, it knows I'm going to return an expression and it evaluates that expression once again, automatically for me, right? And the Erlang system will not do that. In the compiler, I can do it. So macros are compile time. And they really work. It means I wrote an LFE evaluator to run it. And looking at some of the macros people have written, I am overwhelmed that it actually worked, right? Much more than my simple tests. But it works. And it's Lisp 2, which for Lisp people means that variable namespace and function namespace are different. In Lisp 1, they're the same. In Lisp 2, they're different. Schemes typically Lisp 1, because they're the function name and the variable name's the same. It's the same space. Common Lisp is Lisp 2. And I found, in my opinion anyway, Lisp 2 better suited fitting together with Erlang, how Erlang functions work. Erlang functions are sort of neither, right? They're sort of Lisp 2 plus, but Lisp 2 was closer. I know other people have done Lisp 1s instead. And it means it is as fast as Erlang, which is not surprising because it just generates normal Erlang code through the compiler, through core and everything like this. So it does compile down to core Erlang. And what I've got here, these are the actual core expressions in LFE. And if you remove the ones with red over them, they're the actual core expressions in core Erlang. So it was very easy to choose a mapping there which was practically one-to-one. I added an if because I didn't want to use normal Erlang if there, so I added a Lispish type if there. And I can't, this was a pity. Yes, I can define local functions, but they're recursive local functions. So the namespace they work in is recursive. I cannot define them not to be recursively defined, local functions. So I had to fix that myself, which is really strange. It's not a big fix, but just not there. Match lambdas and lambdas, well, they sort of both exist, right? Depending on how you look at it. Maybe I should put the red line over lambda instead, because in Erlang, the match lambdas always have pattern matching, so that depends. But it works, it's fine. It did everything I wanted to. But the limitation is I changed the language to fit into the Erlang system and accepted those limitations and those features. Well, I forgot to mention, I had a very, very nice feature. I got patterns. So of course, pattern matching is part of the language, right? So I've got them, right? It's a waste not to use them. So there, you restrict the language to fit the implementation, or to fit the underlying system. And as I say, it works. The next language I'm going to talk a bit about is I call Erlang. Finding a good name for these things is actually worse than implementing, right? Yeah, so if you think the names are corny, I quite agree, but I cannot think of anything better. The next one was actually worse, but yeah, we'll see. So yeah, I did Erlang. And it's a standard Prologue. I, of course, had to do a Prologue, seeing where Erlang came from, I had to do a Prologue, right? So this is a Prologue there. And in this case, the semantics, of course, are completely different to Erlang. There's nothing here about trying to map the semantics over. They're just extremely different. So just accept the fact. So for example, Prologue has backtracking. So if you can make a choice, if it later decides this was a bad choice, you can go back and make another choice. It has logical variables. So I can fill in holes and I can pass them around and I can fill them in later. And it has unification, which we don't have. amongst other things. So here, the problem was, I want these features. I do not want to change the language. So I have to put, how do I get these features into Erlang? And data structures were quite easy, which is not surprising, again, seeing where Erlang came from. So we've got Erlog atoms are Erlang atoms, no straight there. Erlog numbers are Erlang numbers, lists are lists. Erlog or Prologue structures, like this one here, they map very nicely onto tuples. There is no problem doing that. So the data type mapping is very simple in this case, except for one thing, for logical variables. There exists nothing in Erlang which looks like or behaves like a logical variable. Right? Okay, syntactically they look the same, but the behavior is completely different. So they are global in a sense, and they are mutable in a sense. They're not freely mutable, and I can change them, but I can take this variable and I can give it a value. And if I give that variable value, everyone else who sees that variable will get that value as well. So it's global and mutable. I can unify them, right, which I can't do with Erlang variables. So I can say x equals y. Now neither might have a value, but I know that in the future, if one of them gets a value, they'll both get the value because they're unified and put together. Right? This is something else. And changes, in this case, are seen everywhere. So I might unify 10 variables together, and one of them gets a value, and suddenly all of them see that value. So I have to do this type of thing. And there was no corresponding Erlang data structure which matches. But we could be cunning. Right? We could use a tuple here of one element, which did not match anything here. Because here, there had to be, in Prologue, there has to be at least one argument, one element inside here, which meant the tuple here is at least 2 elements. So we could use a tuple of one element for the variable. Right? So we could use that in the index. But seeing these are global, we have to keep them in a global table. I cannot just pass them around and bind them as they go, because then the variable bindings won't go. So we have to keep those in a global atom table or a global variable table, which can either be a dict or array, depending on how you want to do it. And this is quite nice in one sense, because one feature Prologue has is that when you're backtracking, variable bindings get unbound. So when I backtrack back, if I backtrack over a variable binding, the variable gets unbound. So the next time I can try it, get another value. And keeping them in a global table, a dict or array here, and keeping these tables in the stack, when I unwind, I just automatically throw away the latest versions and get the old version back again, and everything's fine. So that actually made it quite simple to do some things. But it also meant that when you're building these things, in this case it was just an interpreter, it could be a compiler, I just never got around to it. You have to carry around some state containing, amongst other things, the atom table, or the variable table. Other things you have to contain is a database as well. So Prologue has a database. I haven't mentioned it here in the slide, but it has a database, and that is dynamic, and that's also global. You need to carry that around with you as well. I found a dict actually worked better than ets tables. I tried both, but the way Prologue accesses that table, when you add and remove things from it, it actually worked easier with a dict. If you wanted to use ets, you had to become much more cunning to do things to make sure. It's just the way the logical database is defined, right? So if I'm backtracking, if I'm working with something and someone else changes under me, in some cases I'm not supposed to see those changes until later. So if I bung that straight into an ets table, it can get difficult. So there, again, kept in a dict worked well. Okay, backtracking. So this Erlang was an interpreter, which does all this. I'm not going to show code examples of backtrack from this because it's pretty hairy code working on the Prologue semantics. It's quite straightforward in one sense, but if you know what it's doing, it's quite straightforward, put it this way. But Erlang does not have backtracking, which is a shame, right, in a sense. So as we know, once we make a choice, we have to stick with it. So if you've got a function definition, you call a function, once you've chosen a function clause, that's the one you've got. Same thing with a case or an if. You cannot go back and try again afterwards. Yeah. So it's unfortunate, and sometimes it's a nice feature. Sometimes we'd like to do that. We like to try something, go forward and see if it works, and if it doesn't work, go back and try again. It's not easy, it's not difficult, but we have to do it, but we have to do it ourselves. So this is just an interesting, I think, an interesting feature. So we can do backtracking ourselves here. We will use continuations to do this. So at every level we'll say, when I call a function, I will pass an argument and say, when you're done, call this function. Just keep on going. So we always keep going forwards, 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 forwards. So at a top level here, we've got some succeed fun here, which returns succeed in a value. And when we call find solution, we've got our data we're putting in, and we pass it the succeed, what to do. So it knows that find solution knows when it's done what it's supposed to do, it will call the next. So here we have an example which is not doing backtracking. It's get A here, it's got data, it's got the next, it does some stuff locally, just a normal Erlang call here. We're not going to backtrack over this one. The nice thing about here is we can choose what to backtrack over. We don't have to backtrack over everything. And our next is taking this next and doing some more stuff there and passing that on. So we're passing the next that came into us on and we're doing some more stuff before it. So we're chaining that through the whole time. And here we do our more stuff here with our data and the next after that. So now we know that more stuff A here, when it's done, it's going to call this one, which will then call that one, which will then call what came in here. So we're building this, all the way we're going down, we're building this chain of functions. So we're never really, from the backtracking point of view, not returning. So if we want to backtrack, what do we do then? Well, we set up a choice point. So we do some stuff here, and here is a choice point, which is a list of funs to do. Right? So we'll do this, then we will do one of these. And what that means is we'll try the first one. If that succeeds, we're done. If that fails further on, then we'll try the next one. If that
That's not how Prologue backtracking works. You have to try all of them.
well, it does it sequentially.
It's not that it succeeds. You have to keep the choice point even if
Yes, I do that. Okay, yes, I don't do that. Assume it cuts. Okay. Otherwise, it gets very messy. Right? We only want one solution in this case. Actually, I can handle multiple solutions. I can do that.
how do you implement find all?
Right. There's a problem. I'll mention that. I'll talk about that. The choice point function is very simple. It's so simple it's disgusting, right? So we take the first goal, the first fun, we call that, and we've defined to say that if we succeed, we return the tuple succeed in a value. So if we succeed, we just return that value and pass it up to the next level. If it fails, then we return fail, and we call ourselves recursively to get the next element, next goal in the list. So we try each goal. If it returns succeed, we just pass it on back upwards again. If we return fail, and if we run out, we just return fail. The problem here, the problem with this is that there are a couple of problems here. Is that when we hit the end, we sort of call, then walk out at the bottom here, and we've got this big stack of stuff here. And how do I keep track of things where I get there, right? If I want to do the find all, I get all these solutions. I can get one solution. I have to put it somewhere, then I can fail and get another solution and put it somewhere. That's the problem with this implementation. I can put it in the process dictionary. I can store it somewhere else or do something. I have to put it somewhere to keep it. Right. If I want multiple solutions, then I can do find all. It's not.
Also missing the bindings here.
Yeah, that's the next problem. I'm not going to take that up because that'll take about 10 more minutes. Right, so I'm not going to talk about that.
This is the issue.
Well, no, this actually worked.
Oh, it does work.
Yes, it does. One of the features of Prologue, the Prologue syntax, is that the grammar is definitely not LALR1. It's actually a backtracking grammar. So in the worst case, you can look at the very first token and decide is that an operator or not an operator, and I cannot tell until I get to the end whether it was, right? So you get these strange cases. And this is how I wrote the Prologue parser, using this data, and that works, right? It works because of the data. In this case, I don't need variables, Prologue variables. You can fix it so you don't need Prologue variables. Prologue variables put another layer on this. You have to pass around some variable structure which you chain through in the same way, and you bind variables in there. I've done it, but you can do it. It's messy, but it works. This gives you not backtracking anyway, so I can choose. I like it. Third one, I know. The third one, which I'm working on now, I call Lua. There was no other good name. eLua was already taken, and I think someone else had already got Lua Earl, or Earl Lua was already taken by someone else, so I couldn't find a better one. And this is a goal to implement standard Lua, standard 5.2 Lua. And Lua, if those haven't looked at it, it's a small scripting language. It's designed to be a scripting language, designed to connect it to other systems to do things, typically used in the gaming world. And it's a simple, rather simple little language. It's quite neat. It's imperative. So it's definitely imperative all the way down. It's a dynamic language. Things can come and go, and you'll dynamically search. If you want to call a function, you'll actually go and search for the function definition in a predefined way, so it can change things. It's lexically scoped, and it has mutable variables, it has mutable environments, and it's got mutable data. So we're doing something extremely un-Erlang-y here, right? It's a small language with only a small number of data types. So it's got a nil, which they use for no value or false or a lot of other things as well, right? Seeing there's so few things here, they tend to use everything for everything, right? So nil means a lot of things. They've got booleans, true and false. They've got numbers, which are just floating points. And they've got strings, which are pretty much like binaries. And they've got tables, which are mutable key value tables. And they use tables for everything. They use them for tables, they use them for arrays, they use them for lists. It's the kitchen sink, anything they put in a table. And the thing with a table is it's global. So if you make a change to a table, anyone else is referring to that table will see that change. Right? So it's a global data type. It's global data, and it's mutable global data. And that means you have to manage global data. There is just no way around it. At least with the Erlang, it was very restricted and was hidden behind the back. Here it's very explicit. And the only way to do that is you need a global data table store. You need somewhere you need to keep a global store of tables so everyone refers to it. So, for example, you can use an ordict, you can use an array, or you can use an ETS table for it. ETS tables didn't work very well with a naive implementation. I'll show you an example later why. It has mutable environments. So the environments, they also behave like tables. So you use ordicts. They work very well because they're generally quite small. I've got my tables. And internally in the table, they do, as I said, they do funny things with them. So they're using numeric keys from 1, 2, 3 upwards. They treat them as an array, right? And they treat everything else separately. So I'm working now with a structure where a table, it consists of an array for those and an ordict for the rest. That seems to work very well. So this is basically what my global state looks like here. So it contains tables here. Here is a table store. Here's the next free table number. I'm just using indexing into them, numbers. And, well, this is the list of free tables. So if I've had a table and I've freed it, it goes back in here. And here's the next number if there's nothing left in the free list. This meta, certain data types have metadata. So here's putting in which are tables. So here's the various metadata for various types. Here's the current environment, which is a stack of environments, which are tables. And here's just a unique tag, so I can do catch and throw and make sure I'm not doing catching something else, right, which I want. So yeah, that works fine. So I'm going to give you a quick code example, I'm done. So this is the function which, when I get a table, I have a key, get the value for that key in the table. Right, this is the code for it. So it's get table key, and the first argument is the table here, which in this case, it's a reference to a table. I cannot put the table, I have to put a reference to the table, because the table's global. And here is the key, and here is my state. And I have to check seeing I'm handling numbers specifically, I have to check if it's a number, and then I check if that floating point is actually an integer value. Is it 1.0, 2.0, etc.? And if it is, I call the integer keys, otherwise I call with the key keys. I couldn't find a better name. If it's not a value, I just call the key keys, and if it's something else, I go in and check, does this thing have a meta table, or meta table method? So if it does, if it has a meta table with that object, and there's the key which is called __ index, I go in and find it. If there isn't one, then it's a legal index. If it is one, I use that, and I use that to try and find the value. So it's very step. And we see exactly the same thing when I'm actually referencing a table. So if we've got the normal key here, I separate the table, there's a meta table. So each table has a meta table. And there's the table itself, which is the value. I try to find it in the value. If I find it, I just return it with the state, which in this case hasn't changed. If it's not there, then I try and find a meta method for it within that table. So I keep stepping down. If you can't find it, you go in and try and find a meta method for it. And you actually keep going round until you find the actual value at the end. And with the integer ones, I extract the array part, and I do exactly the same thing there. If I can't find it, I get the meta method. We're almost done. Getting the meta method is looking up the meta method of __ index. So if there's a meta table there, it will try and find the __ index value of that and use that. And if it's not there, we just return nil because we couldn't find it. If it's there and it's a function, it then calls that function and returns the return value. Okay. If it's not a function, it's something else, then we call get table key recursively on that with the same thing. So if it's a table, we can actually step around table. We look at the tables meta table, and then the meta tables meta table, and keep on going. And you can actually put them in a loop as well too, and it'll crash. So if you want to enjoy yourself. That's that. And that works. That's it. That describes very well exactly how it's based. These things are just macros, so I could test different table implementations. Doing this does not work very well with an ETS table, because when you read in the table in this case, you're reading in the whole table. And that could be hundreds of elements big, which is very inefficient doing it in ETS, because you're writing them backwards and forwards. In ETS, maybe if you were to combine these two operations into one, perhaps you could have it as a bag or something like this and match out of it and get it going better. So that's that. The final slide. If I want to set something like this, this is the function for setting a key here. So I get the table. I've got the table here, and I'm trying to find the key. If I find the key, don't ask me why they do it like this exactly right. I don't know. I'm just trying to work out what I do. If I find the key, I just replace the value. Okay. If I don't find the key, then I try and see if there's a meta index. If there's a meta table with a key __ new index. And if there's that, then I use that to store the value. If there isn't, then I just put it straight back into the table, and I replace the table, fix up the tables in my state, and return the state. Right? So this is the type of thing you have to do if you want to work with global state. Right? You have to carry it around with you all the time. It is not very blindingly fast at the moment. I will grant that, but it does work, and it does actually do most of the language. I haven't got meta tables for user data yet, but we'll get there. Final question. Well, final thing I want to say is this useful? Can you use it? I mean, is it something I could actually plug into a system and use it? And I definitely think you can write other languages on top of the Erlang VM and use them. Some cases you can get them very fast, some cases you won't. And it just very much depends on what you're doing. So for example, in the Lua case, if you have some Lua code and you will need to run it, but it's not very much, and you don't want the troubles of packaging up a Lua system and including that in a release and everything and interfacing that, then you can use something like this. If you're running a lot of Lua code It depends on what type of code you're running. If you're running lots of small functions, then this is probably quite as fast, almost as fast, because I don't have to copy data from out to the Lua system. I can run this directly in Erlang. If you're running big functions, doing a lot of computations, then this is definitely not an option. So it depends very much. Yeah. So just some things on implementing languages and how the choice of language and the features of language affect the implementation and what you can get out of it. Unfortunately, there is no way around the immutable data in the system. And I hope they don't change that. Sorry. Yeah. Okay, that's it. So.
Thank you very much.
Yeah. Questions? Yeah.
I think we have time for just one question.
Yeah, grab me afterwards if you want.
One consequence of putting all your tables into your global state
Yeah.
is that the garbage collector can't touch any of them. If you want any garbage collection, you have to write your own garbage collector in Erlang. Have you thought about doing that?
Yes, I have, and I've done it. Well, in some, it depends a bit on the. Sometimes you can see, for example, you're unwinding the call stack, and then you can see there you can free those, and you can free tables. Sometimes that is not good. So yes, I have a garbage collector, which will run through and remove tables from the table store, and then let the Erlang garbage collector collect them. Right? It seems a bit off. I would need that actually in the Erlang system as well for the variables, so I could keep. Now I have to do a backtracking style to do that. If I had a garbage collector there, I could do a forward-going style the whole time. Yeah. Okay, that's that. Okay, right.